So we finished out talking about the main features of electric fields, and in particular the field lines, which show you the shape of the electric field at each point in space. And again, the idea there is we started off this chapter really not knowing much about what an electric field was. We know that charged objects do something to the world around them. They kind of change things around them because if the object was not charged, it has no effect or influence on the things around it. As soon as it becomes charged, here's what I'm looking for, it does have an influence. It starts to move things around it. And so we want to try and put a face or a name to that thing around it. We call it the electric field. And electric field lines let us turn that invisible thing around charged objects into something visible. That's what these pictures here are showing you. This is the effect or influence these charged objects have on the world around them. Gauss's law is an observation about the relationship between electric fields that influence and the charges that create those fields. And it's a very general law. It says something about any arrangement of charge you want to put together and the field it creates. But because it's so general, it's also very hard to get your head around the first million times. So we're going to do a little bit more with that today. The original thing we did was just count manually. So we tried by hand to count up all these field lines, but there's a couple problems with that. The first is the number of field lines I chose to draw is completely arbitrary. As long as I just make sure that a charge that's twice as big gets twice as many field lines, which I did do, this minus 2q got twice as many as this plus q, and I follow all those other rules of field lines, this is just a schematic. It's just a representation of what's going on. The actual electric field is something that doesn't change depending on how I draw the field line. So we really want a way of counting that doesn't depend on my picture I drew. It depends on the underlying field I'm trying to describe. And that's why we need the math that we're dealing with down here. The other thing is that even if we had a really detailed picture, drew lots of field lines and tried to count this thing up, that's so much to count. So if we have a way to compute it instead, we can actually skip over that step. So that's what we're attempting to do here. And I have some of my props now, so I'm going to start trying to use them. So we first thought of, it's hard to count up mathematically the amount of field lines passing through an entire surface, through the entire grocery bag enclosing these charges. So let me take my scissors and cut out a little piece, a little rectangle of that bag, a patch of it, and ask how many field lines just pass through that part. So that's what we're seeing up at the top right. But also I have a little bit more of a visual of it now. Not saying it's high budget, but it's just a little piece of plastic. That's all it is. But think of it as a part of that bag, a little patch of it. What's this Nerf dart? It's that normal vector. It's saying which way is outward. It moves with that patch. If the patch is facing towards you, the normal is facing towards you. If the patch is facing to the right, the normal is facing to the right, and so on and so forth. So it's our way of tracking which way is this facing to know whether a field line is poking into or out of it. And here's going to be one of my field lines. It's just a stick, but see, it can pass through the patch. That's what's going on here. And you can see in that case, it lines up with the normal vector. That's the direction of the outward. That's saying it pokes out through the patch. What angle would it have to be at to this patch so that it's not poking through, it's grazing the surface of the patch? Does that look
90?
like it's grazing? Yeah, I think I heard 90. Yeah, 90 degrees is where it's grazing. So then, what if it's not at 0 or at 90? What would you say about that vector? Is it passing through or not?
Yes.
I'd say it is, but stop thinking of it as a yes or no, even though I phrased the question that way. Think of it as a how much is poking through and how much of it is grazing the surface. You can take this vector and break it into a piece that is poking through and a piece that, I don't want to bend it that far, but grazing the surface. And that's kind of counting it more properly, saying how much of that vector pokes through and how much of it grazes the surface. And that's what we get by finding e cosine of theta. It's how much of the field actually sticks through, the component of it poking through. The other thing that we talked about is what's going to make more field lines pass through that patch. What are our options? So we just talked about alignment. That's going to make sure that more field lines pass through if they're all like this. If they're all grazing that patch, then they're not passing through. What else makes more field lines pass through my patch?
A larger area.
Larger area. So here's my larger patch. Look at it, it's catching more of those field lines down there. It doesn't have its normal vector on, it's kind of naked, but there's that new larger patch. What else could I do?
Would like a stronger electric field
Yeah,
create more field lines
what's that going to
through?
look like in terms of this right here? Stronger fields mean what about the field lines?
Maybe more.
Yeah, there's
Like
going to be
they're
more of them. They're going to be denser. They're going to pack in. And so you look at this current picture, how many are passing through the patch right now, which I can fit about one through it right now. If I put nails in between all of these gaps, I filled in the field, made it denser, I'd catch more than just one field line. Okay, so all of those things increase how many poke through that patch. And we call that count we've got of how many poke through the flux through the patch. So that's what this is right here. It's a capital phi, Greek letter phi, for flux. So that's done for the patch. We know how to count how many field lines pass through a single one. So now let's come back to the original question. How many pass through an entire surface? Well, if we know how many pass through just one patch, how would we figure that out?
Figure out how many patches are there.
Yeah, you just break the entire surface into patches, count how many field lines pass through each of them, and then add all of those fluxes together, all of those counts up to get the total count. So add up all of the little counts of field lines, how many pass through each little patch, and that will give you the total count through the entire bag, through the entire surface. Remember, our technical term for that bag is a Gaussian surface. The number of field lines through each patch. And I just figured out how to count that. For any one of those patches, you just calculate this right here. This is the orientation of that field relative to what? The angle between the electric field and what in particular? Theta, what's it measuring the angle between? The electric field and what?
Is it the patch?
Yeah,
Or
what
like the
about the patch?
Like
bag?
What
the
feature?
surface of the patch?
Not the surface, because then say theta is 0. That's going to mean that it's grazing, but cosine of 0 is 1, meaning we get a large number out. That's a little bit opposite to what we're trying to do. Because if it's grazing, we don't expect any lines poking through. Why are we getting a large number for that? It's this normal vector. That's the nose of the patch. The direction it's facing is what's important. So not the patch itself. It is a feature of the patch, but what we're trying to describe is whether the field pokes into or out of it. And in that case, it's more important to say, is it along the normal, in which case it pokes out? Is it grazing, so perpendicular to the normal, in which case it does not poke out? Orientation of the field relative to the normal of the patch. Normal is another word for perpendicular, like normal force. And last thing is the size of the patch. The very last thing is that this is going to depend on which patch we're looking at. All of these things will. So the strength of the electric field around that patch. So I'm going to use an index to say it can be different numbers for different patches. The angle the electric field makes with the normal to that patch can be different for each patch. And the area of each patch can be different. So all of those are not a fixed number. Now we can do some trickery to make sure that they do end up equal a lot of the time, and that saves some trouble with the math, but they're not guaranteed to be. So for this one right here, this patch, would you say that that flux through it is a large number or 0 or what?
I think it'd be closer to 0.
So that electric field vector, and it may just be the perspective of the drawing, but it is actually grazing that surface. So no lines pass through that patch. So we would expect 0 flux. But let's see. So this is roughly the normal to that surface. Remember, perpendicular. So that's just saying it's perpendicular to the surface, and I'm trying to draw a little square there, like a right angle. It is at 90 degrees to the surface. What is cosine of 90?
0.
0.
0. Good. It better be. Because again, I'm using this to count how many lines pass through that patch. When that angle is 90 degrees, the electric field grazes the surface, I get 0 out. Seems like this count works. It does what it's supposed to. So in this picture, this is a flux through that patch, so a little delta phi of 0. It is grazing the surface. All right, now we come to, this is actually the one that we looked at the very beginning of the page. So I'll sketch in my normal again. It's something about like that maybe. That's about perpendicular to that face. What would you say about this flux? Is it 0 or not 0?
Not 0.
Not 0.
Not 0. That line is poking out of it. It might not be perfectly aligned, but the angle is not 90 degrees. It's actually closer to a 0-degree angle between those two vectors. And so here we're expecting a positive flux. We're expecting this calculation to come out to a positive number to agree with the fact that that line pokes out of that patch. All right, and finally, we'll come to this one over on the left. So the normal vector might be something about like that. Again, I'm just trying to draw the vector perpendicular to that patch. What would you say about that flux?
I can't really tell, but it looks like it might be somewhere in the middle.
Well, so what does the field vector do for this patch? Does it poke in, poke out, graze? What's it doing?
It pokes in.
It pokes in. So this is actually an angle larger than 90 degrees. What's cosine of an angle larger than 90 degrees?
Would it be negative?
Negative. Look at that, though. It works. If a field line's poking in, we get a negative count for the flux. If a field line's poking out, we get a positive count. If it's grazing, we don't get anything. That works exactly like what we did up here. We just don't have to do it manually anymore. This calculates it for us. The angle is greater than 90 degrees. For this one, the angle is less than 90 degrees. And as a result, we get a flux less than 0 here. This field line is poking in. This is also how they do lighting in video games and any other computer rendering stuff. You have to find the normal to each part of the surface because there's this thing called the law of reflection that says light coming in bounces out at the same angle it came in at, but they measure that angle relative to the normal direction, the outward direction of that face. So there's computations like this happening all the time anytime you play a game. We have come up with our way to count how many field lines pass through a surface. We're now going to attempt to do that for a specific charged object, in this case, a point charge. So what I've done is I've trapped him in this Gaussian prison right here, this bag. And I'm going to try and show a visual of this. Again, it's pretty low budget. The Earth right there is my point charge. This clear ball around it is the Gaussian surface enclosing it, the bag I've trapped it in. And you can even see the little rectangles. Those are my patches. So at each part of this surface, imagine little normal vectors poking out. It's sort of like a ball it's got little spiky hairs poking out in every direction. Those are all the normal vectors saying what is outward for this surface. And we're going to attempt to count how many field lines pass through this bag, find the flux through it. So we add up all of the electric field poking through each little patch. How much of the electric field pokes through each little patch. And I'm going to look at a couple of these patches on this surface. So like over here, the patch is always, it faces outward. That's what it does. When you're standing upright on the Earth, so you're 90 degrees to the Earth's surface, aren't you standing kind of like that? You're facing outward like that. So this is the normal direction right there. If you're standing over here, standing upright would look like that. If you're standing up here, up at the North Pole, it looks like that. So that's how I'm figuring out my normal vectors, is if I stood on this surface, which way is my head facing? And it does depend on the surface I draw. If the Earth were a very weird, crumbled up ball kind of shape, then standing upright would look a little different. I'd be facing different directions than I am in this picture. So what I need to do is measure the angle between that normal direction and my electric field, which is the red lines. What would you say about the angle between the normal vector and the electric field at any point on this surface?
The angle would be 0.
The angle is 0. They line up with each other. These lines really stick out of this surface. They don't have any sort of grazing component to them. They stick perfectly out of the bag. And it's because we've sort of lined the bag up with the shape of the electric field. We've enclosed something that has sort of a spherical symmetry to it, and our bag has spherical symmetry. So these vectors line up with each other. The reason that's really good is because if theta is 0 for every single one of these patches, then cosine of 0 is 1. And that means I've simplified this calculation a little bit. Now I just add all the electric fields passing through each little patch. I don't need a cosine because they perfectly pass through. And I can actually simplify even a little bit more. What would you say about the strength of the electric field? So I compare how strong the electric field is here versus over here versus over here. Do you think it's stronger at any of those points?
No, they all look the same.
Yeah, what in particular is the same about each? What
Like
determines
the
how
magnitude of each vector.
the magnitude of each, but I'm saying
The
why is the electric
distance
field
from
the
the
same? The
charge.
distance, yes. I'm the same distance from the charge in each case, and that's what determines the strength of the electric field of a point charge. How far away are you? Now what I can do is that number E is the same for every single patch. I don't have to have an index, it's the same number. I can pull it out of that sum because it applies to every little patch. And it doesn't need an index anymore. So this step was because the electric field is the same for every patch because we're the same distance away from the charge. All right, so now I'm trying to calculate if I multiply the electric field strength on the surface by this thing right here. That will count how many field lines pass through that surface for me. What is that thing that I just put a bracket on? What does it represent? It's saying add up the area of every little patch making up this surface. If you add up all those little areas, what do you get? I break this surface into little rectangles, little patches. I find the area of any one of those patches, and I add it up with all the other areas. What area do I get? The whole area of the bag, of the surface?
I want to say that, but I feel like there's more to it, or is that just it?
That really is it. Yeah. I'm just saying if I take each of these little areas, I add them all up over the entire surface, that's just the surface area. That's the area of that sphere. So this is the surface area of the bag. And we know how to find that for spheres. You may not remember this, but at some point it's probably been said. Surface area of a sphere is 4 pi times the radius squared, where the radius is that right there, the radius of the sphere. So it's a sphere, and that's why I wrote that. All right. I also know the electric field strength for a point charge. It's something we've already determined previously. It's this number K times how big the charge is over how far away you are from it. This, I said, is because the electric field of a point charge is KQ over R squared. I'm multiplying that by this surface area. I can cancel some stuff out. So I get 4 pi K Q. And that almost is what I want. The very last observation is to remember K can also be written as this number, this epsilon 0 thing. This is from very early on in the chapter. When we first introduced Coulomb's law, I said you could write that constant out front of it in terms of either of these things. I'm just going to write it in terms of the one on the right because it makes this whole thing look a lot simpler. So if I replace K with that, the 4π's cancel out. And I'm left with this Q thing over here. So this all comes out to, if you have any room left, the size of the charge over epsilon 0. So let's look at the far left-hand side of what I did and the far right-hand side. This was to find the number of field lines passing through the bag. On the right-hand side, I have a number. So this is just a number. It's some value you can calculate. And then this is the charge inside the bag. I took out the absolute value because if we had a negative charge inside the bag, the flux, the number of field lines should be a negative because all of them will poke in. So this is a more general purpose way of writing it. Charge inside the bag. Read that off. The number of field lines passing through that bag is proportional to, is a number, a multiple of the charge inside the bag. That's Gauss's law. That's this right here. We just turned it into a mathematical statement. It is an equation we can work with now. We have only done it for a single charge in this example, but it's pretty easy to generalize to any amount of charge you want. You just imagine doing this multiple times with multiple individual charges. You add up the electric fields of each. That will give you the overall flux. And then you add up how many charges are inside that bag. That will give you the overall charge. So if more than one charge is present, Q is just the net charge enclosed. And I'll add a parentheses here. A lot of times we write that as Q enclosed. So, and honestly, it's good I'm recording this because Gauss's law is the hardest thing in the semester. Once we get past Gauss's law, it'll take a little bit of getting used to what comes next, but I really feel like people internalize it a lot better than Gauss's law by the end of the semester. So it's good that you can come back to this. So I'm going to use this now. Now Gauss's law is a tool I have to work with. It says that if I can just find a way to count how many field lines pass through a surface, that will automatically tell me how much charge is inside, and I can go the other way. If I know how much charge is inside of that bag, I immediately know something about the electric field on its surface. And that's the way I'm going to use it for this page. I'm going to know the charge and use it to find something about the electric field for something new. In this case, it's going to be a capacitor. So I got to tell you what a capacitor is first. It's just two metal plates with equal amounts of charge but of opposite sign. I don't have a good way to justify to you why the electric field looks the way it does here other than to show it to you and say, see, that's how it looks. So that's what I'm going to do. If you remember that oil where we put the little grass seeds in, I also did that with a capacitor. In this case, these two coat hanger pieces, they're long, straight metal plates, essentially, and you'll see what the field looks like in the middle. There it goes. What do you notice about it?
Like they're trying to,
Yeah. And the lines are pretty straight, right? They're more or less going straight across. They're not spreading like we're used to seeing for field lines. So that'll give me my first hint of what the electric field looks like. It kind of just goes straight across. And remember, field lines point away from positive charge towards negative. This one is inside of this surface because I'm going to need that surface here in a minute. Okay, so it's actually inside that cylinder. The cylinder is my Gaussian surface, my bag I'm going to use in just a minute. But this is what the electric field looks like inside. You would call that a uniform field. meaning the strength of that electric field is actually the same everywhere inside. You know that because you don't see the lines spread out and you don't see charge really moving in one spot while it's just barely moving at all in another, as long as you're in between the plates. So if I come back over here, you can see now the bottom half is a little bit obscured by some seeds from an earlier thing, but you can kind of see that bridge that's forming. Except you actually do notice at the far edges of the plates, so the top and bottom of the image. What do you notice up there and down at the bottom? Not many seeds are congregating up there, and it's not as good at forming those bridges across. Okay. It forms them pretty well in the middle, but not so good at the top. What's that telling you about the strength of the electric field up there?
Not that strong.
Yeah, it's weaker. So as we move towards the edges of the plates, the field is weaker, meaning the lines spread out. And they actually do curve. I can't really show you that in this video. It's hard to see, but the lines do curve if you get towards the outer edges of the plates. And we call that the fringe field because it stops behaving in this nice uniform way. So what we've got so far is the symmetry of the plates results in a uniform electric field, but the fields at the edge behave differently. That's the fringe field. Once we finish talking about this, we're going to forget the fringe field exists because it's more complicated and it's not even in the part of the capacitor we're interested in, what's going on in between the plates. But the final question is, what's going on outside of the plates? So not at the edges, but like look at the far left and far right in this video. Do you see much at all going on out there?
No.
No, there actually isn't much of one. Right, so that's our picture of the electric field, and over here is just a side view. And at the edges, you start to get this fringe field. This other video I'm going to pull up is to help you see the fringe field, that curving of the field a little bit better. And to do that, I'm going to come back to the idea of a test charge. I'm going to hold something down between the plates and see what happens to it, and then compare to what happens if I hold it outside or around the edges of the plates. These pith balls are just a way of putting charge onto something, and it'll stick around for a while. The plate on the left is positively charged, and the plate on the right is negatively charged. So when that pith ball first hits, in this case, it looks like the positively charged plate. It'll pick up some positive charge. What's it going to do after that as a result?
Be attracted to the negative charge.
Yeah, it'll both be pushed away from the positive plate and then pulled towards the negative plate. But then it's going to hit the negative plate. That'll neutralize out the positive charge on its surface, and it'll actually become negative. So what will it do then?
Repel.
Repel. But then it's going to hit the positive plate again, pick up positive charge, repel, hit the negative plate, pick up negative, repel. So what you're going to see is it'll bounce back and forth. But it stays pretty well in the middle because the field is uniform. It doesn't curve, and so the ball doesn't get launched out. Now, it might because of something I do, but as long as I can keep it in the middle, it should pretty much just bounce back and forth. You see it jumping back and forth, and then it's actually forming some sparks. The camera really doesn't like this one. Like when I do it in class, the camera shuts down for a second because it's not well shielded. We'll talk about that soon. Oh, shoot, did I not do it in this one? Well, I think I'll have to show you that part of it in person, but what ends up happening is if I hold that ball over here, it swings around the outside. You don't have to draw this. This is just to illustrate. But you're going to see it swing around and then back, and around and then back. And it's because it's following that curved fringe field instead of the nice uniform field in the middle. I'll bring that one in on Friday. There's another one I also want to save for in person. Anyway, we know the direction of the electric field now. We don't know how strong exactly it is. We want to get an expression that tells us about that. So the field does point away from the positive plate and toward the negative plate, but that's about all we know of it at the moment. We're going to use Gauss's law to figure out how strong exactly this field is in terms of how much charge is on the plates. That'll be one factor. What else do you think determines how strong this electric field is?
Surface area.
Yeah, the size of the plates. So the area of these. And we'll see exactly how it depends on those two things here in just a bit. I'll go ahead and actually spoil the answer just so we know where we're headed. It's going to be the charge on the plates divided by this number epsilon 0, which, remember, it's just a number, 8.85 times 10 to the negative 12. It's a number that we need so that when we put in a specific charge and a specific sized plate, we get the correct value for the electric field. It's a conversion factor, more or less. What does this say? The more charge you have on the plates, what happens to the strength of the electric field? If I have more charge on the plates, are you expecting the field to get stronger or weaker?
Stronger.
Stronger. Good. This is in the numerator. That says the bigger it gets, the larger the electric field gets. That makes sense. All right, if the plates get bigger, but the amount of charge doesn't change, what do you think happens to the strength of the electric field?
It gets weaker.
It gets weaker because that
Weaker.
charge is spreading out. It's less densely packed. Okay, good. The larger the area, the smaller the electric field because it's in the denominator. We're dividing by a bigger and bigger number. And so that really is a statement about the density of charge. So sometimes you see this written where Q divided by A is its own value. We call it the surface charge density. We use sigma for that. So it's just how tightly packed the charge is on the surface of the plates. But you can calculate using either one. You could calculate Q divided by A first, or it could be given, and then use sigma over epsilon 0, which I forgot a little 0. Or you could just directly use the charge and plate area. Okay, so that's where we're trying to get to at the end of all of this, and we'll see if Gauss's law does it for us. I mean, you'd be pretty surprised, or else I'd be pretty bad at my job if it didn't, but let's see how it gets there. So what I've done is taken a bag, and I've actually embedded it in this plate on the left. I'm allowed to do that because it's an imaginary bag. I can put it through whatever I want. But it's got these little patches making up its surface, and they've got all these different normal vectors, which just say what is outward for each part of this bag. And what we need to do is see, well, does the field line up with that or does it not? Because that'll tell us, is it poking out or is it not? And I'm going to break that into 3 parts. I need to find the flux, the amount of field lines passing through the front face, through the sides, and through the back face. For the front face, add up how much electric field passes through each little patch making up the front face. Each little patch making up the front face is facing to the right in this picture. All the normal vectors for every little patch on that surface, they're all facing to the right. The normal vectors are saying, if I was standing on this surface, which way is my head facing? If I were standing on the side of this thing, my head's facing to the right, and that's going to be true no matter which part of it I stand on, because this surface is flat. So all my little normal vectors face to the right. What is the angle between that and the electric field, which is the red vector?
Just 0 degrees.
0 degrees. They're both in the same direction. If they're facing the same way, there is no angle between them. So I can pull the same trick. Theta is 0 everywhere on this surface. So cosine theta is 1. And so I really just have to calculate this thing right here. Add up how much electric field poke through each little area. They all poke through it. They don't graze, but I need to figure out how strong the field is now. But the electric field of a capacitor is uniform. It's the same strength everywhere in between the plates. So that value of E is going to be the same number no matter which patch I'm looking at. So I can pull it out of this sum. The last thing is just add up all these little areas, all these little patches making up the front face. I'll just call that the area of the front face. I could say it's the area of a circle, but I picked a kind of arbitrary shape to embed in this surface. I could have used a big box, or I could have used a pyramid or something else, and I would still get the same value. This kind of just keeps it generic. It didn't really matter which shape I used. So I just end up electric field times the area of the front face. And that's my first step. I'll need to do something else for the back and sides of this Gaussian surface to count how many lines pass through them. Any questions on this? All right, well, hopefully we will finish this never-ending chapter next time. And then I get to give you another 16, 17 pages of notes for chapter 19. And then for chapter 20, it's like 20 pages of notes. For some reason, they're just massive chapters in this course. So we don't cover a full 10, we cover something like 7 or 8, just because the first 3 are enormous for some reason. All right, I will see y'all on Friday. That, I will say, is in person because I'm hoping a lot of the ice clears by then. In the meantime, I don't think we've got anything because, again, this chapter is just so long. I want out of it too, and we're almost there. Any final thoughts, final questions?
So thank you. Be safe.
All right, thank you, you too. Everyone hears me now, right? We're good?
Yes.
Yeah, I can
Okay.
hear you.